Let's do it. Okay, so today I'm going to finish chapter 5, what I wanted to do in chapter 5, induction. So today I'm going to do so-called strong induction and the well-ordering principle. Let me remind you of what we saw. Now it's almost, well, it's a little over a week ago. So we saw induction, principle of induction, which is the following, which is, again, a fundamental proof technique, a fundamental property of the positive integers. And it's the following. So suppose that let's write it as a property. We know you might remember we can write it as a a result about sets, subsets, but let's write it as properties. So suppose that a property P satisfies the following. Yeah, I'll start with a base integer. Okay, so the first thing is that P of B is true. And the second thing is that if P of N is true, then P of N plus 1 is true. So if both of these hold, then, so if both 1 and 2 hold, then P of N is true for all N greater or equal to B. Okay, so this is the more general version that I stated. It's convenient because you can start anywhere you want. Okay, so this is the principle of induction, which is, again, a really fundamental proof technique and a fundamental property of the positive integers. However, it is not always easy to apply in all situations. So there are certain situations where it looks like a job for induction, but this is not going to work. So I'm going to show you some examples here. And this is why we need alternative versions of the principle of induction. But what I'm going to do, these two things that I'm going to show you are completely equivalent to the principle of induction. They're just variants, okay? So let's just write this. So sometimes, so in certain situations, this version will not work. Okay, so let me show you a typical example where it looks like it's a job for induction, but it's not going to work, but we'd still like induction to work in a sense. And so that'll motivate the versions that I'm going to talk about today. Okay, so here's an example. So show that, I don't know why I have the strange feeling that I did this, but maybe it's last year. I'm getting COVID confused. Show that every integer greater than 1 is the product of primes. So you remember that this is part of the fundamental theorem of arithmetic, right? So the fundamental theorem says every integer greater than 1 is a product of primes. It also says that this product is unique, okay? So I just want to show that every integer is a product of primes. So this is sort of silly because you might already see that induction is not going to work very well, but if you don't see it, that's fine. Let's just try to do it by induction, okay? So let's try to do this. So proof by induction. Let's try this. Okay, so so P of n will be n is a product of primes. That's my property, and I want to show this for n at least 2. Okay, so I'm going to start at 2. Okay, so P of 2 is clearly true because 2 is prime. So by product, of course, we mean it could be just a prime itself. That's fine. Okay, so now suppose that the statement is true for some n. What can you say about P of n plus 1? Now, you want to show that n plus 1 is a product of primes, knowing that n is a product of primes. If you watch the video that I recommended you watch on Thursday, you may have had at least this intuition that factoring and addition don't mix very well, and this is a good example of this, right? So knowing that n is a product of primes is not going to help you at all in figuring out that n plus 1 is a product of primes. So the induction hypothesis here is useless. Okay, so this will not work. Okay, so the principle of induction is not going to work here. Not in this form, but in fact, the proof is not very difficult if you use just a slight variant of the principle of induction. So we need an alternative. So here it is. Okay, so the first alternative to the principle of induction is so-called, and I hate that name. It's such a bad name. But it is known under the name of strong induction. It's a really bad name because it's not strong induction. It's just induction phrased differently. Okay, so this is so-called strong induction. Note, this is not stronger than the principle of induction. Okay, so it is not a stronger statement, and you shouldn't get the impression also that, oh, I'm just going to use that since it's strong induction, I'm just going to use that all the time. You can try, but I personally try to avoid this strong induction at all costs. Personally, that's I maybe there is an example somewhere where you really have to use this version, but if I have to use strong, I mean, if I can't use regular induction, I'm going to use the well ordering principle, which is the next thing we'll see. But that's my personal preference, but we'll see. Okay, so what is strong induction? Okay, so here's our first. In the book, they give you three different, I think they give you three different versions of strong induction, which are more and more general. I'm going to start with the second one, and I hope I don't mess it up because it looks a bit, it's not difficult, but it looks a bit weird the first time you see it. Okay, so here's the theorem. Okay, so let b be an integer. Okay, and suppose the property P, so it's going to look a lot like regular induction. Okay, so suppose property P satisfies the following. 1, P of B is true. So up to this point, it's exactly the same, right? There's absolutely no change. Second, this is where there is a change, and this is where the word strong comes from, is rather than suppose, so in regular induction, you say, okay, if P of n is true, then P of n plus 1 is true. If it's true for an integer, then it's true for the next. here what we're going to do is we're going to make the hypothesis that it's true from B right up to a certain integer. And if it's true from B right up to a certain integer, then it's true for the next. So we're making a stronger hypothesis in the induction, in the second part of the induction. Okay, so if P of B, if P of N is true for all, sorry. This is where, okay. So if P of K is true for all K from B to N, then P of N plus 1 is true. Then the conclusion is the same as induction, is that P of N is true for all N greater or equal to B. Okay, so this is so-called strong induction. Okay, so what I'm going to do is before I use it to prove my fundamental theorem of arithmetic, let me just illustrate this in the simplest setting possible. Okay, so here's the idea. So so to use strong induction, and let's just take B equals to 1, okay, just to make it really, really simple. Okay, so first you show that P of 1 is true. And then what you do is you suppose that P of 1 right up to P of N are all true. So you're not only assuming that P of N is true, but it's actually true for all values from 1 up to N. So you make a stronger induction hypothesis here. So you suppose that all of these are true, and then you show that P of N plus 1 is true. Okay, so this is what you want to do. Now, if you think a few minutes about it, about this, you'll see that it's basically the same as just regular induction. Okay, so because so idea of idea, if that makes any sense. Okay, so you have that P of 1 is true. Okay, then if P of 1 is true, then it means that P of 2 is true. So now you've got that P of 1 and P of 2 are true. So P of 1 and P of 2 are true. And by the second property, it means P of 3 is true. So now 1, 2, 3 are all good. So 4 is good. So 1, 2, 3, 4 are good. So 5 is good. You see the idea, right? That's it. Okay. So there's really nothing really new here. Okay. So rather than just assuming that the result, the property holds for N, you just suppose that it holds for all integers up to N. And then you can use all of that to go to the next. And you see that you're not making an extra hypothesis here, because if induction works, then this has to work too. Okay. All right. So let's see. Is that okay? Does that, you see what I'm talking about, right?
Yeah.
Yeah. All right, good. Okay, so let's use that to prove the existence of our, so back to fundamental theorem of arithmetic. Okay. So I'm going to use strong induction. So proof. Man, I hate that. By strong induction. I mean, if you read grown-up math papers, nobody calls it strong induction. As I've never seen the, so people will just say we use induction, and they will specify clearly that their induction hypothesis is that whatever, property they want to prove is true from B right up to N, okay? Okay, so we've got that P of 2 is true. We had that. Now suppose that P of 2 right up to P of N are all true. To show, I have to show that P of N plus 1 is true. Okay, maybe you see now that, so the problem is that going from N plus 1 to N in terms of factoring is totally useless. There's no known connection between N and N plus 1 in terms of their factors, okay? But certainly if I know that the property is true for all integers less than N plus 1, then I'll be fine. So how do I do it? Okay, so case 1 is N plus 1 is prime. Then we're done, right? If N plus 1 is prime, I've expressed N plus 1 as a product of primes. Case 2, N plus 1 is not prime. Brain power, eh? Is not prime. So what does it mean that N plus 1 is not prime? It means that it is the product of two integers which are greater than 1 and less than N plus 1. So there exist integers A and B such that N is equal to A times B, and both A and B are bigger than 1 and less than N plus 1. All right, so that's what it means to be that N plus 1 is not prime. What's my induction hypothesis is that in particular P of A and P of B are true. Okay, so by induction hypothesis, P of A and P of B are true, right? Because they are strictly less than N plus 1, bigger than 1. So induction hypothesis, they are both true. What is that? It means A and B are product of primes. So A and B are both okay, both products of primes, and thus so is N plus 1, which is equal to A times B. Is that okay? Hopefully I didn't go too fast. I think this is sort of straightforward, right? So N plus 1, if it's prime, we're done. It is a product of primes. If it is not prime, it is a product of two smaller numbers. And my induction hypothesis now is that every number less than N plus 1, at least 2, are products of primes. So I just put them together and that's it. Okay, is that okay?
That's good.
All right. Okay. So if you understood this, you see that it is a job for induction in the sense that you reduce to checking to smaller values, right? Except that you can't just go down to the previous one. So you just assume that it's true for everybody below, and then when you go down, everything works out. Okay, excellent. Let's do another one before I state the horrible version. There's another version of this. I was trying to avoid it, but I'll just do my best. But let's do another example of this. Here's a game. So this is a game with two players, and they play one after another. There are two piles of matches with the same number of matches. Okay, so what's a turn of this game? A turn, a player must remove a non-zero number of matches from one pile. So a player removes a non-zero number. That's not very elegant, but number of matches from one pile. So any number of matches, but at least one from one of the piles. Okay, so that's a move. And then the other player does the same. And who wins? The player who removes the last match. Okay, so we'd like to show that player 2 has a winning strategy. So show player 2. This is not a difficult problem, okay? Player 2 has a winning strategy. Okay. So let's think about this a little bit. So there are two piles of matches, and same number of matches, like that. And the first player will pick one of the piles and remove a certain number of matches. And then player 2 responds. Okay. If I'll bet that some of you already see how to do what the strategy is. And if you don't, if you spend 2-3 minutes on it, you will find the winning strategy. So to give you a hint, if you haven't seen it already, think of it, if suppose that there's exactly one match in each pile, then player 2 is very happy, right? Because player 1 will have to take a match from one of the piles, and then player 2 removes the last match after. So that's easy, right? So if player 2 can get everything down to one match in each pile, player 2 is happy. So suppose that player 1 has removed 3 matches from this pile. What would be the response for player 2? That seems like a smart move.
3 matches from the other pile?
Correct, right? So if you balance things out, so if player 2 removes 3 matches from here, you'll be left with the same number of matches in each pile, but less. And you repeat and you repeat, and eventually either player 1 will be very silly and remove everything from one pile, or will eventually leave one match, and then player 2 will win, right? So hopefully you see this. So now I'd like to show that this works. Okay, I want to do a good job as a mathematician. Okay, so P of n will be the statement player 2 has a winning strategy when each pile has n matches. Okay, so we'll starts at 1. Okay, so I'd like to show P of n for all n. Okay, so to show for all n P of n. Okay, so I'm going to use induction. I'm going to use the strong version. You can probably see why, because if player 1 removes many matches, then we're going to go way below n, right? So the hypothesis on n is no good. So I'm going to make the hypothesis that player 2 has a winning strategy for every value below n+1, and then I'll be happy. Okay, so we use so-called strong induction. Okay. All right. So here we go. So P of 1 is clearly true, right? I mean, if player 2 has to take one match from one pile, leaving only one match. So player 2 takes that match and wins. This is obviously true. Okay. So now let's assume that P of 1 right up to P of n are true. Show P of n plus 1 is true. Okay, so that's what we want to do. There you go. Okay, so that's what I want to do. Okay, so I have the two piles, and we've figured out that the strategy is pretty simple. Okay, so player 1 removes some matches from one pile. Okay, let's remove the case immediately. So if all matches of the pile are gone, player 1 wins, right? Player 2, sorry, I keep saying player 2 wins. Right, that's clear because player 2 can now remove all the matches from the other pile, and that's it. It's over. Okay, so now, suppose that the pile still has, let's say, A matches. Let's call it M matches. So M is at least 1, but it is less than n plus 1. Okay, because player 1 has to remove at least one match. Okay, so then player 2 removes matches from the other pile, leaving the same number. That's the key. Leaving M matches. Okay. So now we're back to an instance of the game. So now we are in the instance of the game with M matches in each pile, right? And what's our induction hypothesis? It is that whenever you have less than n plus 1 matches in each pile, player 2 has a winning strategy. So since P of M is true by induction hypothesis, right, player 2 has a winning strategy. And that's it. Okay. Hopefully this makes sense to you. Yeah.
So basically here the argument would be we assume that there's a winning strategy for a smaller game.
Yep.
So then by the player 2 removing the same amount of matches, it reduces the n plus 1 game to a smaller game,
Yes.
which we assumed is true. So
Exactly.
P n plus 1 is true.
Yep, exactly. So player 1 is stuck into the smaller instance of the game. So must lose. Yes, absolutely. Okay, that's good. Yeah. Okay. So that's the game right there. Now I'm going to show you yeah, how do I want to do this? Okay, let's do it. What the hell? Yeah, because there are many questions that use this verse. So here's yet another. So here is a slightly generalized version of strong induction. Okay, so let's try to explain how this goes. It's the same thing again, but it's just stated in a slightly different way. Okay, so now what we're going to do is so sometimes in certain situations, you know what? Okay, I have a good idea. I'm going to start with the example to illustrate what we need, and then I'll state the principle, and then I'll solve the example. Okay, so SWOT, why is it needed? Here's an example, and this is a classic question. Okay, so prove, here's the example. So prove, this is not a difficult question, by the way. I mean, it's just really a question of formalizing things properly. So prove that every amount of postage of 12 cents or more can be achieved using only 4-cent and 5-cent stamps. Okay, so what does this mean? It means that let's say you have to send a letter and it costs 43 cents to send the letter, and you have 4-cent and 5-cent stamps, but you have as many as you want of each, you can actually get the right postage amount for your letter. Okay. All right, so let's just take a look at some small values. So 12, I mean, the first value is clear, right? So 12. Okay, so 12 cents. I'm using 4 cents and 5-cent stamps. That's 3 4-cent stamps, right? 3 times 4-cent stamps. Okay, yeah, suppose I try to do it by induction. Okay, that's what I want to. So this would be my base case, right? I start at 12. Okay, and now I say, okay, let's suppose that, okay, so let's try with, and whether it's strong or regular induction, at this point you see it's not going to work. Okay, but by not much. Okay, so let's try with induction. Okay, even strong induction. Okay, so suppose that P of 12 right up to P of n are true. I didn't write what P of n is, but P of n is I can achieve n using 4 and 5-cent stamps. Okay, now we need to prove P of n plus 1. But you see, it still doesn't work, or does it work? Actually, why does it work? No, it doesn't work, but it's very tricky. Okay, so who can find the bug? If it looks like it works, because you say, okay, remove, let's say 4 from n plus 1, and I've got a smaller value, Okay, I'm going to write that. Okay, there's a very subtle mistake in the argument. Okay, so here's the idea, and this is wrong. Okay, I mean the idea is right, but the argument is wrong. So okay, so you say, okay, look at n plus 1, remove 4. Okay, so this is less or equal to n. This is less or equal to n. So P of n plus 1 minus 4 is true. So add 4 cents, 1 4-cent stamp, and we are done. It looks right, but there is a problem with this. Can you're marking my copy. This is what I wrote, and you have to mark my copy, and you're really happy to put a big fat 0, but you have to tell me why I got 0. Why is this not correct? What is the problem with this argument? N goes by increments of 12. Yeah, all 5s. Okay, good. You spotted a problem. N goes by increments of 12. Not quite, but sort of. So I'm going to try to say what you're both trying to say, but look at the case 13 cents. I mean, my argument has to cover the case of 13 cents, right? Where's the proof for 13 cents? There, it's not there. Because if I do 13 minus 4, I get something which is less than 12, and I can't use my induction hypothesis. Okay, so here's the problem. Uh, 13 cents, even 14 cents, and in fact 15 cents, none of them are not covered by this proof. Right? Because when I'm subtracting 4, I have to remain above 12. Okay, since n plus 1 minus 4 should be greater or equal to 12 for the induction hypothesis to be valid. Right? So I can't, and you have the right answer. But what if you prove those separately? That's what you need to do. And that's exactly it. Okay, so this is my more general version of strong induction. It is not in the induction hypothesis. It is in the base case where you have to prove maybe more of them, and that's it. So you see here, if we prove 12, 13, 14, and 15 separately, after that, the argument I tried will work. Okay, so notice, however, that if we prove P of 12, P of 13, P of 14, P of 15 in advance, then our argument is correct. All right? So that's it. So that's the trick. Okay? But you have to be very careful when you're doing something like this, right? If you're going to below, you can prove like really bad things if you're not careful. Okay? So yes, that's the trick. So you prove 12, 13, 14, 15 to start. That will be your base case, will be those 4. And then you say, okay, now I take anything which is, if it's true for anything right up to a certain point, including those 4, if I subtract 4, then I'm okay, right? So in the worst case, I'll fall in those 4 cases, and I know they're true. Okay, so let's state the more general version that I want to state. So here's the strong induction general version, which is what I've tried to motivate with my example. Okay, so suppose, okay, so let B, so again, I can start anywhere. Let B be an integer, which is an integer, and I'm going to, so in my example, I went from 12, 13, 14, 15. I had these four basic cases. So I want an integer to encode that if you want. So I'm going to call that J. Let J be greater or equal to 0. So J equals to 0 corresponds to strong induction, the first version I've shown you. Let's add that in. Okay, so here, so the J equals to 0, that is strong induction as seen earlier. Okay. So suppose that the property P satisfies this. First of all, P of B right up to P of B plus J are true. Okay, so I'm showing several consecutive cases that I want to show starting at B. I have J plus one of them. Okay. And 2, if, okay, this is, I have to be careful how I state this. Okay, yeah, no, all right, okay. If P of B right up to P of N are true, N has to be at least B plus J, right? You have to go at least up to B plus J. Then P of N plus 1 is true. So if both these two things are true, then P of N is true for all N greater or equal to B. Okay, it's still a bit complicated. It's more complicated than the previous version, but somehow I think I've stated it in a way which is, I mean, if you look in the book, it's not stated quite, it's the same thing, but I think my version is better. But anyway, okay. Yeah, I like that. I like this version. Okay, so hopefully you see, I think the example is a good one to keep in mind to see what the idea is here. Okay, so let's so this is true, and I'm not going to waste time showing, but I mean, how do you prove that? You use induction to prove that this is true. It's the same thing as induction. Okay, so let me add a remark here. This is a theorem proved using induction. Now, you might say, wait, but if you're proving this by induction, why do you need to use a bit? Yes, true. Okay, it's just that it's a more efficient version to use, for example, for the stamp thing. But you can prove the stamp thing using induction, but it's just that your proof will be very, very painful. So this is like a more efficient version to use in certain cases. Okay. Okay, so let's go back to our example with the stamps. So 12 cents is 3 times 4 cents, 13 cents. That's 1 5-cent stamp plus 2 4-cent stamps, right? 14, that's 2 5-cent stamps plus 1 4-cent stamp, and 15 cents is 3 times 5 cents. And now you see it's over because for the next one, you just add 4. And if you add 4 all the time, you'll just get all the numbers after, okay? So, and after that, just add 4 cents. In fact, there are many ways because you could add, for the next one, you could add 5. I mean, there are several ways of doing it. But, or maybe it turns out to be the same. I don't know. Anyway, so here's the proof. Let me write down the proof. So proof using strong induction. So B is 12, just so you have the parameters. B is 12 and J is 3. Okay, so that you can see how this goes. Okay, so P of n, the statement is n can be obtained with 4 cents and 5 cents. Let's just write it like that. You see what I'm talking about? Okay, so P of 12, P of 13, P of 14, P of 15, they're true. Right? So we saw that earlier. That's easy. Now, suppose that P of 12 right up to P of n are true, and n is at least 15. Now I want to show P of n plus 1. Okay, so what do? I subtract 4. Now this is n minus 3. If n is greater than 15, at least 15, then n minus 3 is greater or equal to 12. Which is making us happy, right? So it means that P of n minus 3 is true. So P of n minus 3 is true by induction hypothesis. So n minus 3 is a sum of 4 cent and 5 cent stamps. So I add back a 4 and I've got n plus 1. Okay. I mean, the argument, I mean, I hopefully you see that this is very, I mean, it's easy, right? So once you've got 12, 13, 14, 15, take any number after that, you remove 4, you're going to fall within something that you know is true. So you can add a 4 cent stamp and so on and so forth. Okay. So the argument is very simple. So it's just a question of formalizing it. Okay. But hopefully you see, and that's all it is, that there's nothing, nothing new here. Oh, I really like the way I explained it with the example. It's this. I'm so proud of myself. Okay. Questions up to this point? I'm almost done. Good.
I don't quite understand the 4 part. Like, why do we do minus 4?
Because I could have, okay, because, yeah, sorry, I didn't explain that very well. It's because I can use a 4 cent stamp. So if I have a certain amount, I subtract 4, and I know that the amount now that I get can be obtained with 5 cents and 4 cent stamps, then I can just add a 4 cent stamp and I've got the number.
Oh, okay, thank you.
Yeah, that's where, yeah, sorry, I didn't make that. That's where it comes from. Yeah, let me add this. Okay, so the trick is if I can obtain M with 4 cents and 4 cent stamps, then I can obtain M plus 4 with 4 and 5 cent stamps. Right? Just you add a 4 cent stamp. That's all it is. In fact, yeah, so what this says is, in fact, you don't need more than 3 5-cent stamps. You can do it with 3 5-cent stamps, and if you have an infinite amount of 4-cent stamps, you'll be able to do it. Right? Okay. All right. So let's move on to well, let's just change pages. The well ordering principle. Okay. I'm going to state the well ordering principle, and you're going to say, this is the most obvious thing I've ever read. Yeah, so here it is. Every non-empty subset of the natural numbers has a least element. Right? So you're going, yeah, of course, right? So you take a subset of the natural numbers. If it has at least one element, it has the smallest one, right? So this is something that is burnt into our brain, our understanding of the natural numbers. So this is the same thing as induction. It's just a different way of stating. This is, so note, this is the same thing as induction and strong induction. They're all the same. They're all just different formulations of the same principle. So different formulations of the same property. So the most elementary version of all of them is the well ordering principle. I mean, you can't get cleaner than that. Every non-empty subset of the natural numbers has a least element. Okay. It is an exercise in the book that I've assigned to show that these three principles, principle of induction, principle of strong induction, and the well ordering principle, that they're all equivalent, that you can prove one from the other. Okay. It's a good exercise. Okay. Not the easiest thing, but it is. Oh, is there a question? Sorry, somebody has a question.
I was just wondering, when you say a non-empty subset, is that a finite subset or?
Nope. Any subset. I'm not saying it has a greatest element, but it must have a least element.
Oh, these are positive
Yeah,
numbers.
not the integers.
Oh.
Yes. Yeah, that's important.
Okay, that explains it.
Yeah, yes. Yeah. If you change that for Z, then this is not true. Yes, absolutely. Yeah. Okay. Notice that if you take the rational numbers, let's say the positive rational numbers, the well-ordering principle is not true there. You can find non-empty subsets of the rational numbers that don't have a least element. Now, if you want to come up with one, that's maybe a little harder. But for example, okay, let me add that in just for the very curious side. So note, if we change n to q plus, not true anymore. So if you take a bunch of you can find sets of positive rationals that don't have a least element. Can anybody see how to do that? This is not super easy code like that. So here's an example. Consider the set S of all x such that x is a rational number, x is greater than root 2. Right? So S contains, so this is, okay. So S contains 1.4, 1. No, that's a bad example. I mean, it's a good example, but I don't want to illustrate it like that. You can find rationals which can approximate root 2 to an arbitrary degree, right? You can get closer and closer and closer and closer to root 2 from the right. So the limit of these numbers will be root 2, but you can always find a closer and closer one, right? So exercise, I don't know. You can try if you want. So this one, yeah, you have the right idea. So but you have to tweak your idea, but that's sort of the idea. Yeah. So you can find rationals which are just to the right of square root of 2, which is not a rational. And then you can find another one in between. Ugh. Okay, so here. I'm sorry. Okay, no. I was clicking on my computer. Wow. It is time for this semester to end. Okay, anyway, that's not my point. My point is that this is the most flexible of all the versions that we've seen, okay? Because we can apply it in all sorts of different contexts, and we will be using it when we're going to do graph theory quite a bit. Let me show you one application of the well-ordering principle. Here's an example. It's not the easiest one that we're going to do today, but I will finish with this. So if you remember the division algorithm, okay, so now I just need you to focus just like less than 5 minutes, and we're done. Okay, so recall the division algorithm. If you take any a integer and any d positive integer, there exist q and r such that they are unique, but we've proved uniqueness already, such that a equals qd plus r, and r is greater or equal to 0 but less than d. Now, I'm sure you believe this because we've played with that so many times that you understand how this works, right? You divide by d. But if I want to prove the existence of q and r formally to make sure they exist, we need to do it properly. And the well-ordering principle is the simplest way to show it. Okay, so existence, Okay, I'll put this. Oh, sorry. I don't know if I've ever introduced this. Maybe not. There exists unique. If you see this means there exists a unique, but I don't like to use it. I mean, I don't mind, but I don't use it. Just one less thing to worry about. Okay, but you might see this. So if you see exist with a exclamation point means there exists unique. Okay. So proof of existence using the well ordering principle. Okay, so here's how this works. So let S be the following set. It's the set of all X integers. Yeah, let's just put integers, not to confuse anything, such that X is equal to A plus B times D for some integer B, and X is greater or equal to no. Sorry, I'm gonna do it like that. Okay, so what is S? It is the set of all. Sorry, I don't want. Damn. I need this to be X is in Z such that this and X is greater or equal to 0. Yeah. Z plus doesn't contain 0. Annoying, but okay. So what is S? S is the set of all non-negative integers that can be written as A plus a multiple of D. I consider this set of all these numbers. Okay. I claim that S is not empty. That's what I need this to apply the well ordering principle to say it has the smallest element, and that's the number I'm looking for. Okay. Now I know that, I mean, you are looking at the hardest part of the proof. Whatever I'm going to do after this is easy. Okay. So this is like, how did somebody come up with this? They had a good day. Okay. So you look at the set of all combinations of A and D, and you just need actually multiples of D. You look at all these numbers and those that are greater or equal to 0. So the first thing I need to show is that S is non-empty because, let's just go here. Okay. So why is S non-empty? So how do I produce numbers like this? So if A is greater or equal to 0, then this is okay. So obvious if A is greater or equal to 0, because then A is in S, right? You just A plus 0 times D. Okay. What if A is negative? What do? I want A plus BD. I want to choose B such that A plus BD is greater or equal to 0. A is negative. But then I can pump up D. I can just add as many Ds as I can until I go above A. So just take B big enough so that A plus BD is greater or equal to 0. Do you see this? So let's say A is minus 15, then D is non-zero. So I can just add as many Ds until I go above A, right? I can just, right, take a million times D. Yes?
Could we make just D negative A? And then,
No, D is fixed. D is a positive. It's the divisor. It's what we're dividing by.
Okay.
Right? So it's fixed. Yeah, D is fixed. A is fixed. The only thing I can choose is B. Okay, so I mean, yeah, is that okay?
Okay.
Yeah. Okay, so S is non-empty, so it has a smallest element, and that's the R basically. So by the well ordering principle, S has a least element, and I'm going to call it R, and it is in fact so what do I need? Sorry, so what I need to do is to show that this is less than D. That's the only thing that's left to do. I'm sorry, yeah, this is complicated. Okay, well, hang on. Okay, so we need to show that R is less than D. Notice that A is equal to, yeah, crap. Okay, so notice R is equal to A plus BD means that A is equal to R minus BD, right? So A is minus BD plus R. This is the Q, right? That we're looking for. If this is the correct R, I've chosen it so that it is greater or equal to 0. That's that by construction of my set S. What I mean, what I need to make sure of, English bad, it is that this R is less than D. This is really complicated. Damn. Now I really wish I was live, not on a video screen. Okay, I'm gonna finish this. If you're lost at this point, I guess it's totally normal. Sorry. Okay. Okay. So I want to show that R is less than D. So why is R less than D? So R is the smallest element in this set S. Suppose for a contradiction that R is greater or equal to D. Okay, so recall R is the smallest element in S. You have to remember that. Okay, so R is equal to A plus B times D for some number B. And it is greater or equal to D. That's my hypothesis for a contradiction. Do you see what to do? If you're still with me, that's fantastic. But there's just one last thing to do. I want to contradict the fact that R is the smallest number in that set S. That can be written as A plus something times D and still be greater or equal to 0. Do you see what to do? Okay.
You subtract A?
Yeah, almost, but not A. So I want to look at numbers that look like this and are still greater or equal to 0. So if this whole number is greater or equal to D, I can remove one D and still be in the set and greater or equal to 0, right? A plus B minus 1 times D. Agreed? I've subtracted, yeah, I've subtracted D from both sides. So this is still an S, but smaller than R. That's a contradiction. Okay, this is Yeah, I need to find a better example of how to illustrate the well ordering principle. This is too complicated. There's too many things flying around. It's unfortunate because actually this argument is used in the very same argument is used in very cool stuff. But yeah, anyway. Okay, so if you want to forget what I just did, try to. That's fine. But don't forget the well ordering principle. We'll be using that. But there's tons of examples in the book of how to use it. Okay, you'll have to use it, figure out which one is the best of all these. But I'm going to show you. So let me add this. So in the section on graph theory, chapter 10, the chapter. That's chapter 10. We will be, but it's going to be much easier than this. We'll be using the well ordering principle often. Okay, so it's a very common argument used in graph theory. If you're looking at so the word graph here does not mean graph of functions and has absolute zero connection to those. Not at all. It's a completely different thing. Okay. So that's it for today. If you have questions on this, sorry about the last part. It's way too hard to do in video. Questions, comments? All good? Okay.
Yeah, I think so.
Was that, sorry?
I said yes, I think so.
Okay, all right. See you all then tomorrow.
Thank you, sir.
Thank
See
you.
you.
sir.
Bye-bye.
Bye, see ya.
Goodbye, sir.